The differentiation of trigonometric functions is the mathematical process of finding the derivative of a trigonometric function, or its rate of change with respect to a variable. Common trigonometric functions include sin, cos and tan. For example, the derivative of f equals sin is represented as f equals cos. F is the rate of change of sin at a particular point A. All derivatives of circular trigonometric functions can be found using those of sin and cos, since they can all be expressed in terms of sine or cosine. The quotient rule is then implemented to differentiate the resulting expression. Finding the derivatives of the inverse trigonometric functions involves using implicit differentiation and the derivatives of regular trigonometric functions. Derivatives of trigonometric functions and their inverses. Proofs of derivatives of trigonometric functions. Limit of sin, theta as theta goes to 0. The diagram on the right shows a circle, center O and radius r. Let theta be the angle at O made by the two radii OA and OB. Since we are considering the limit as theta tends to 0, we may assume that theta is a very small positive number, 0 less than theta 1. Consider the following three regions of the diagram. R1 is the triangle AB, R2 is the circular sector OAB, and R3 is the triangle AC. Clearly, using basic trigonometric formulae, the area of the triangle AB is the area of the circular sector OAB is, while the area of the triangle AC is given by collecting together these three areas gives. Since r greater than 0, we can divide through by 1/2 r2. This means that the construction and calculations are all independent of the circle's radius. Moreover, since 0 less than theta 1, it follows that sin greater than 0, and we may divide through by a factor of sin, giving. In the last step we simply took the reciprocal of each of the three terms. Since all three terms are positive, this has the effect of reversing the inequities, e.g., if 2 less than 3 then 1/2 greater than 1/3. We have seen that if 0 less than theta 1 then sin theta is always less than 1 and, in addition, is always greater than cos. Notice that as theta gets closer to 0, so cos gets closer to 1. Informally, as theta gets smaller, sin theta is squeezed between 1 and cos, which itself is heading towards 1. It follows that sin theta tends to 1 as theta tends to 0 from the positive side. For the case where theta is a very small negative number, -1 theta less than 0, we use the fact that sine is an odd function. Limit of -1 theta as theta goes to 0. The last section enables us to calculate this new limit relatively easily. This is done by employing a simple trick. In this calculation, the sine of theta is unimportant. The well-known identity sin 2 theta plus cos 2 theta equals 1 tells us that cos 2 theta 1 equals sin 2 theta. Using this, the fact that the limit of a product is the product of the limits, and the result from the last section, we find that limit of tan theta as theta goes to 0 using the limit for the sine function, the fact that the tangent function is odd, and the fact that the limit of a product is the product of the limits, we find derivative of the sine function. To calculate the derivative of the sine function sin theta, we use first principles. By definition, using the well-known angle formula sin equals sin alpha cos beta plus sin beta cos alpha, we have, using the limits for the sine and cosine functions, derivative of the cosine function from the definition of the derivative. To calculate the derivative of the cosine function cos theta, we use first principles. By definition, using the well-known angle formula cos equals cos alpha cos beta sin beta, we have, using the limits for the sine and cosine functions, from the chain rule. To compute the derivative of the cosine function from the chain rule, first observe the following two facts. The first is a known trigonometric identity, and the second is proven above. Using these two facts, we can write the following. We can differentiate this using the chain rule. But, from above, we can rewrite this as but. This is an identity relating to horizontally translating the sine function, and therefore, we have proven that derivative of the tangent function. From the definition of the derivative to calculate the derivative of the tangent function tan theta, we use first principles. By definition, using the well-known angle formula tan equals, we have, using the fact that the limit of a product is the product of the limits, using the limit for the tangent function, and the fact that tan delta tends to 0 as delta tends to 0, we see immediately that from the quotient rule one can also compute the derivative of the tangent function using the quotient rule. The numerator can be simplified to 1 by the Pythagorean identity, giving us, therefore, proofs of derivatives of inverse trigonometric functions. The following derivatives are found by setting a variable y equal to the inverse trigonometric function that we wish to take the derivative of, using implicit differentiation and then solving for dy dx. The derivative of the inverse function is found in terms of y. To convert dy dx back into being in terms of x, we can draw a reference triangle on the unit circle, letting theta be y. Using the Pythagorean theorem and the definition of the regular trigonometric functions, we can finally express dy dx in terms of x. Differentiating the inverse sine function, we let we're then using implicit differentiation and solving for dy dx. Substituting in from above, differentiating the inverse cosine function, we let we're then using implicit differentiation and solving for dy dx. Substituting in from above, we get differentiating the inverse tangent function, we let we're then using implicit differentiation and solving for dy dx. Left side, right side. Therefore, substituting in from above, we get differentiating the inverse cotangent function, we let we're then using implicit differentiation and solving for dy dx. Substituting into the above, substituting in from above, we get bibliography. Handbook of Mathematical Functions, edited by Abramowitz and Cdang, National Bureau of Standards, Applied Mathematics Series, 55.